So yeah, we're dealing with some fairly lengthy training here because this product is completely new to Pico, completely new to the whole of the channel. So we've got to spend a little bit of time introducing you to a vector network analyzer and to frequency domain measurements and all the sort of S parameters and touchstone files and what have you that go along with that. So there's quite a bit to get through. That's why we've broken this into 2 sessions. Now, dealing with a fairly broad audience across the channel, some of the channel and some of the people here in St Neots are quite technical, and they support the technical questions from the customer. So I've got to try and address some of the technicalities of the product, but it's not technical knowledge that you necessarily need to understand for selling, as you know. We need to be able to sell to the applications that people have. We need to be able to sell this as a solution. So there's a bit of a mix here, and some slides will appeal to some of the audience and others to others. And when we go through the technical stuff, it doesn't matter that you don't necessarily catch it all in these sessions. What you need to know is that the technical backing exists, and hopefully through these slides and various other medias you'll have background reference material to look at when the demand for technical knowledge appears to arise. But you don't need to necessarily catch it all and understand it all from day one. You'll learn as you sell, as it were. What's happening? Yeah. Right. So as I say, we've broken the training into two sections. So part 1 today, I'm going to introduce you to the vector network analyzer, and we're going to talk about wholly characterizing things and look at what that means. Because this is what the vector network analyzer is capable of doing. It's capable of wholly characterizing an electrical component. And as I say, you'll see what I mean by that. We're going to look at the VNA in the context of the scope, because we're all scope people, so we understand scopes, and we're probably fairly capable of understanding what a scalar network analyzer is, which can be a function of a scope, as we'll see. So we'll come at everything from the scope perspective, and I'm also going to come at the whole subject from the TDR TDT perspective, because many of you are already selling the 9300, 9311 in particular, with its TDR and TDT capability. So if we start with that knowledge and move from that, we should do all right. We'll actually build a VNA. We'll describe a VNA in its very simplest form and move that through to what a quad RX VNA is. So we'll build an architecture of a VNA, and then we'll look at what a VNA can tell us in wholly characterizing something, and who wants to know, so that we know who to go and sell to. And then at the end of the session today, I'm going to touch on touchstone data sets, and we'll describe scattering and S parameters, because they're kind of fundamental to the whole of vector network analysis. The second part on Monday is going to be a lot more to do with demonstrating the product, how the product works, how you make the measurements using the product. We'll introduce you to Smith charts. We'll show you how to demonstrate the instrument to its full leading edge performance, and it is a leading edge VNA, despite its low cost. It really is. The importance of calibration and calibration standards. So if you're going to make really good measurements, then we need to fully understand what the calibration is all about and how we need to do it. And then we'll look at some of the more advanced features, and I'll do a competitive comparison with the other VNAs in the market. So the VNA is the Pico VNA106 is what we're selling. What I want to point out is just 4 bullet points down here really. First, it's an all new design. It's fully bidirectional and a full function VNA. Now why are those things important? Because there are, first of all, lots of designs in the market. I'll show you them later. There are lots of VNA designs that are all based on a relatively old, we call it the engine, the innards of the box. This is the way copper mounting got off the ground. They bought a VNA hardware mechanism, put it in a box and sold it. They've moved on from that point, but that's what they did, and various others did the same, and so the whole market knows the planar engine. And that's their first assumption, is that this is the planar engine. No, it isn't. So put that to one side. This is a brand new design. It's designed in the UK for what it's worth, but the design is brand new, and that's how we've managed to enter the market at a much lower price. It's a cost-effective modern design. The instrument is fast, deep and quiet, the importance of which will all become apparent. It's competitive with all of the VNAs in the market at the same 6 GHz level. So you're going to find this box, which is essentially a $6,000 box. It's going to compete with $25,000 VNAs on an equal footing. Won't be like for like in every single feature, but it will compete on an equal footing, performance-wise, accuracy-wise, and we'll see that in the competitive comparison. We'll see what some of the others have got that we haven't got, and we'll see some of the things that we've got that the others haven't got. And then, of course, we're operating at a fraction of that typical cost. So other VNAs lie between about $12,000 and $25,000 full function VNAs for 6 GHz, 6 to 8 GHz. That's the pricing region, and we're down at $6,000. So we're really making a big noise in the market with this product. Now, VNAs, as we've said, well, we've talked about wholly characterizing something. A VNA is an essential tool if you want to wholly characterize any component for its microwave performance. And it won't come as any surprise to you that people designing with these components need that information. They need to be able to measure these components and interconnects and connectors. It's really a toolbox item. Every engineer should have a microwave engineer and high-speed digital engineer should have a VNA on their desk. But they haven't. Even in the big corporations, they haven't. And that's because they're too expensive. And so that's what we're trying to change. We're trying to change that case. We're trying to sell a product at more or less the same price as, say, a 500 meg or 1 GHz scope, which is really the sort of item that every engineer should have on his bench. So this VNA is to go on everybody's bench. So I'm going to play a little video first, just to, or a couple of videos actually, just to emphasize how we have been trying to sell the VNA. They're quite short. They both feature me. I'm sorry about that. But we'll show you these so that we can see the main things that we're trying to sell. First of all, this one's on the website at the moment. This one is how we launched the product in Honolulu, Hawaii at IMS. Hello, I'm Mark Ashcroft, RF Business Development Manager at Pico Technology Limited. We're here at IMS, taking part this year, 2017, in Hawaii, in Honolulu, Hawaii. This is a vector network analyzer. Just like all the other products, this is USB controlled from a laptop in the Windows environment. This vector network analyzer is a 300 kilohertz to 6 gigahertz full function VNA, bidirectional. Got some very impressive specifications here, and I'm going to take that number right out of the picture here. 300 kilohertz to 6 gigahertz, 5,000 S2P points per second. That's very fast indeed, faster than many vector network analyzers on the market. Noise floor 118 dB, and trace noise in the region of 0.005 dB. All of these parameters, all of these specifications are highly competitive amongst all of the other vector network analyzers available on the market today in this frequency range, and yet the price is, well, just a tad under $6,000 US. Quite an impressive price performance point. 8 and 12 term calibration supported. Over here you can see our standards. These are PC 3.5, short open load and through in male and female. We also have available SMA versions that can be used as working standards, but these would be your premium calibration standards, and all of those will be supplied with a full set of data, calibration data. Here's a little example of the software running on the Windows PC here. What we're showing up in the top right, this is a time domain display. We're testing a low pass filter here, and that's the time domain response, or the pulse response of our low pass filter. Here is the, there is the low pass filter. Here is our S21 log magnitude, our frequency response. You can see I've stored into memory the yellow trace there. That's another low pass filter for comparison. And then right down below here you can see the S11 Smith chart for the, or the Smith charts in fact, for the two filters. All of the normal plots that you would expect to be available, the plot formats for all of the 4S parameters are available through the software. We've already mentioned that it has time domain included for that price that we've just seen, just a tad less than $6,000. Time domain not an option that you have to pay for. Notice also that the product has bias tees on both ports. Again, an option that you do not have to pay any further for. Now, this software supports all the usual features that I hope you'd expect on a vector network analyzer. We've got de-embedding and embedding of test fixtures. We've got reference plane shift, all of the normal math functions of a full function vector network analyzer. Okay, so that's Pico at IMS 2017, Honolulu, Hawaii. Hope to see you next year in Philadelphia, 2018 IMS. So there you have all of the things that you need to get across to a customer to tell the customer that this is a professional VNA. We had some brief numbers there. We're going to see a little bit more about what all those numbers mean in a minute. You had some numbers, you had some functionality described, you had CalKit and test lead solutions clearly on display, and that messaging on that stand got a lot of people on the stand and a lot of interest. We've had we've had nigh on 40 orders come in since that IMS presentation, with very little additional market presence of the product. There's relatively little that you need to get across to the customer. Now, I need to try and explain some of those numbers and why CalKits and things are important, but that's the message. what did it take? About 3 or 4 minutes, I suppose. So not a great deal to get across to the customer before they realise that the solution is a real one. It's not a toy. It's not heavily compromised in some way by its price. Now the market is used to things being heavily compromised by price. There are a few so-called VNAs out there that really lack functionality. They're not dual direction, or they don't have the frequency resolution, or they don't have the accuracy, and they don't have the cal kits. Actually, they're mostly real hobbyist type VNAs. Yeah, you need to get across certain things to show that you've got a full solution. Next. So this next video, this is going to it's going to show you what a couple of the measurements are, or what numbers are, and some of the usefulness of the product. Hi, I'm Mark Ashcroft. Let's take a quick run through some of the features and performance of the PicoVNA 106 USB-controlled 6 GHz Vector Network Analyzer. Fast, deep, quiet and portable, the PicoVNA 106, despite its small footprint and its low price, is a full-function 2-port bidirectional VNA, with all the measurement and plot formats that you would expect, and of course, the PC and monitor of your choice. There's nothing left out here. Nominal impedance conversion to 75 ohm, for instance, reference plane shift and embed de-embed are all included, and likewise there's no performance compromise either. This is a low pass filter measurement at 100 Hz bandwidth. No average or smoothing applied here. I have speeded things up a bit here to show you the trace noise and the marker noise over the dynamic range of the instrument, typically down to -118 dB RMS. Performance and value doesn't stop there either. Typically a $2,000 option, Pico includes time domain measurement at the single price. And here we see a comparison of 2 filter responses. Time domain, the pulse step response at the top, frequency domain at the bottom. We need to think too about the trace noise and speed. Supported by trace noise of 0.05 dB RMS. Here I compare 2 short lengths of coax cable, and their readings are coming in at 5,000 full S2P points per second. The software packs in 3 further value-add utilities. Here, P1 dB compression of this amplifier is under test. This at a single frequency, swept frequency also supported. Similarly, phase mod due to AM is supported in a second utility, and a CW signal source utility adds yet more flexibility to the product. Finally, let's pair the PicoVNA 106 with an AC coupled Pico Connect passive probe. Here we're going to make the most of the VNA's speed to browse S21 responses around signal, control, bias and supply nodes of up to 50 volt DC bias around this amplifier. We find there is a -20 dB non-flat swing on the unused input and a -45 dB plateau on a decoupled bias supply, and both were very quickly gathered. There aren't many probes that could even think of going around all of those nodes on a on an amplifier. Probe the whole lot, see them all on a VNA or on an oscilloscope. So you can see there's a connection with the Pico Connect probes as well here. All right, so thank you very much. Right, so but before we try and learn about all of those parameters, we need to understand a bit more about what vector network analysis is, why it is utterly invaluable in nature, how measurements are made and used, what we mean by wholly characterizing, what S parameters are, and what this diagram means. This diagram is right on the front of the instrument so that everybody remembers what these little S11, S21 and S12 are. But of course at this point you don't know, perhaps you don't even know what those are, so hopefully you will by the time we're finished. Right, so here's a 2-port black box with male and female connectors at each end. Actually, this one at this end, this is a female connector, and this one's a male connector. Whoops. Female connector, male connector. We'll talk about that as well. What's inside it? We don't know, do we? Might have an input, might have an output. We don't know which is which, do we? So we don't know, at this point, we don't know anything about that particular black box. We don't know how it will respond when it's connected into circuitry. Perhaps when we do connect it into circuitry, perhaps it's a source of power. Perhaps it's outputting something or inputting, outputting something out of the ports, or maybe something lights up and puts light out or heat out. We know absolutely nothing about that black box. So we're going to try and wholly characterize it in the best way we can. Now, what we've had for a very long time, we've had the famous old DMM, the digital multimeter, and we can usually find some things out about black boxes like this simply by putting a DMM around it. So I did. And so I measured the input port, no volts coming out, no volts AC or DC, measures overload on ohms, 52 picofarads on input cap. The output was pretty much the same, and then I measured it across input to output. Again, 0 volts AC, overload ohms, and 220 nanofarads. Might be a capacitor, might be, but we don't know. We didn't find out much because this particular tool, useful as it is in the toolbox, it doesn't tell us much about this black box. So next I did this, because some people are lucky enough to have a really good source measure oscilloscope in their toolbox. So I got a really good source measure oscilloscope here, and I took a signal from its AWG and pushed it through a power divider such that I could see its signal on the input, the signal on the input. So I knew exactly what was being applied to the input. And then I put another cable on here to see what was on the output. And I arranged things such that I could rotate the DUT and do it the other way as well. So I could put, because I don't know which is the input and which is the output at the moment, do I? So I needed to be able to rotate the DUT as well. And one thing that I've taken particular care on, and you see I had to use multiple adapters to do this, the length of this cable and the length of this cable are very, very accurately the same. You'll see why that's important in characterizing a device. And this is what I got. So I put a 1 kilohertz square wave in blue, and it appears that this device loads it quite heavily at high frequency. So it rounds off the square wave. Okay, tells me something. Seems to load at high frequency and not so much at low frequency. And I got a spike out of the output. Okay. So then I zoomed in, zoom, a long way. And what I found was that the red signal coming out was delayed by about 2 nanoseconds. So whatever it was inside this box, it was causing a delay of about 2 nanoseconds to the signal coming out. Interesting. Doesn't wholly tell me what it is. So I then put a sine sweep in. This is a kilohertz to 20 megahertz sine wave sweep, 20 megahertz at this end, and this is the output. Okay, they looked pretty similar, but I noticed there's a little corner missing down here, and so I zoomed in, and you can even see the individual steps in frequency on here. You can see the little blocks of each step, yeah? And it seems rather like the square wave. There's no load on the input here, big amplitude, then it loads it at higher frequency, and the output has that swept response. I'd say it's some sort of high-pass device. It's passing all the high frequencies. It might still be a capacitor, mightn't it? It didn't pass any low frequencies, so it might still be a capacitor. But we didn't really find out much more about it. We did turn it round, and swapping the ports made absolutely no difference. So it's what's called a reciprocal device. So I'm going to say that's probably passive. There's probably no amplifier in there, because an amplifier, an active device, generally, when you turn it around the other way, you're not going to get the same response both ways, right? There's an input and an output. I'm going to say that's probably a passive device. And what we're doing here is network analysis. We're finding out what that network is. So then what I did, the scope doesn't process the data for me here, but if I take the RMS amplitude of the input and the output, and I plot it as the B wave over the A wave, so every frequency, B1 over A1, B2 over A2, and I plot it, and it's a line that's pretty flat. It's unity gain. It's about unity gain according to those results off the scope. And this is what a network analyzer plots. It doesn't plot these two waveforms. These are the high frequency waveforms, right? It doesn't plot those. A network analyzer plots this. It plots a ratio or a mathematical operation between the A wave, the incident wave, the input, and the output, the B wave as we call it, yeah? So B over A, gain is 1. If you zoom in, what you see is this. So it has no gain or very little gain at low frequency, and then the gain increases to 1. Okay? And the network analyzer, if the scope had the function, would plot that. I guess you can use math waveform actually. You could plot that as a math waveform on the peak scope. So a network analyzer displays a result that is a mathematical operation upon two measurements, an input and an output, or a forward wave and a reverse wave. In this case we plotted gain, and we realized the function of a 20 megahertz, because that's the maximum frequency of the AWG. We have a 20 megahertz scalar network analyzer. We could make a VNA. You could have a 20 megahertz VNA here, because you could analyze phase of each of these blocks. You could measure phase as well, and you could plot phase of each one against as frequency increased, yeah? At each frequency you could plot phase. And then you'd have a vector network analyzer. So it would be possible to make a vector network analyzer out of a scope, and essentially people do. There are some low frequency VNAs that are made by digitizing a waveform directly and providing, say, a VNA up to 300 kilohertz or a couple of megahertz, yeah? And they're used in the power industry. Okay, now we're going to get a bit more serious. We're going to look at time domain, because we know, don't we, Pico knows that we can look at that with a time domain analyzer. The 9311 20 gigahertz sampling oscilloscope has a 50 picosecond high-speed step on it, and we could put a high-speed step in here and see what comes out, or we could see that's TDT, or we could put a high-speed step in here and see what comes back. That's TDR, and the 9311 does that. Now, what I did here, this is a little bit difficult to arrange because nobody makes a high bandwidth 8-channel scope. But so I've simulated this. This is a simulation of a long piece of coax. It's actually this piece of coax, if you like, about that long. And what I've done is I've arranged probing along the coax. Now, I didn't actually do it, I'm just simulating it. But yeah, you could use Pico Connect probes, couldn't you? They're low invasive probes. I could do that, couldn't I? I could put 8 Pico Connect probes along here and stick it into a scope, an 8-channel scope with reasonable bandwidth. And at this end I've got a 1-volt battery, a 50 ohm resistor and a switch. And at this end a 50 ohm resistor, and that's 50 ohm cable. And when I close the switch, what happens is, at the source, the green waveform is this tap here. You can see we get a rising step of a volt straight away. All these waveforms, by the way, would be on top of one another, but I've offset them by 1 division on the scope, yeah? And so what we could see in this display is we could see that step travels along the line and comes out at time periods afterwards. It's taking about 16 nanoseconds to get to 14 nanoseconds to get to the end from the beginning, right? 14 nanoseconds along the line. Okay, what's that tell us? Nothing much. Nothing much. But this is where things get a little bit more interesting. So what I've done now is I put a 1 meg ohm load at this end of the cable. I've mismatched the cable. Now things are a little bit different. When we close the switch, what we see here is 50 ohm cable, and when we first close the switch we know nothing else. We don't know what's at the end of it, or that wave that's setting off down that cable, it doesn't know that it's 1 meg at the end. So it does the same little step, sorry, I said 1 volt earlier, this is half volt step. And travels along the line, and you can see it, here it is, traveling along the line, gets to the end. It still produces, it produces a 1 volt step at the end of the line. What? Half a volt? 1 volt. The reason is that at the end can't absorb the wave, the energy in the wave going along. It can't absorb it. So that energy's got to go somewhere. And what it does is it goes back along the line in anti-phase. No, in phase, sorry, open end. Open end. So what happens here is at the instant the wave arrives at the 1 meg resistor, we do get that 1 volt amplitude despite only sending half a volt. And then the energy travels back. Dunk, 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 dunk. And eventually the source gets to 1 volt. But it does it in 2 steps. And that's how we measure. We measure all sorts of things. This is how the 9311 works. It knows the difference between that green line going on straight and that green line going up. If it goes on straight, we had a 50 ohm resistor at the end. If it goes up, we must have an open circuit at the end. Yeah? So we can find faults on cables, and we can find the impedance of things. We can find out if that's a 75 ohm resistor. We can do all that stuff. And we can also, if anything went wrong in this cable, we'd see it on here. So it's a kind of a network analyzer, isn't it? Let's see what happens when we put the, whoops. When we put a short circuit on the end, this is what happens. Half a volt, half a volt, half a volt, half a volt, all the way to the end. But at the end, the short circuit can't absorb the energy. We can't have voltage across a short circuit. So what has to happen is the edge has to go back in antiphase. and we get no volts as a result of that at the short at the end. But what comes back is ding, 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 yeah, a pulse. And eventually this point knows that there was a short on the end, so we went up to half a volt. 28 nanoseconds or nearly to go all the way to the end of the cable and come all the way back. So actually we generated, at this point here, we generated a pulse. And the pulse widths along the cable were shorter and shorter according to how far they were from the short circuit. Okay, so strange things happen in cables that have length, a length that is relevant to our measurement. Yeah, and I say this because we're going to be thinking with a VNA of relatively high frequencies traveling in cables and traveling in PCB lines, but even on the national grid, 50 hertz is a problem, as we'll see later. 50 hertz traveling along 100 kilometers of cable and coming to a short circuit does some really nasty things. Right, now, complicated case. What happens then if we have a mismatch? I've got 90 ohms at this end, which is a horrible, horrible mismatch, just to emphasize what happens, and 10 ohms at that end. Horrible mismatches. They're all parts in a network, aren't they? We've got a source, we've got a cable, that's 50 ohm, this is 90 ohm, this is 10 ohm, they're all mismatched. What happens when we close our switch? And this is the sort of thing that happens. We can see step, 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 and it goes on as the wave bounces backwards and forwards along this line, finding mismatches at both ends. In order to resolve the mismatches, little steps have to happen. Yeah? And this causes all sorts of trouble if we don't think about how we match a source, a line, and a load. And this is what microwave engineers and high-speed digital engineers have to do. We can see all of this in action when we calibrate a 9311. Let's just do a calibration on a 9311. Well, and what we do here, I'm going to do a TDR calibration, and I've got a load, a known load, and a short. And what we do is we set up our pulse level. So we turn on our pulse, and straight away we can see open end, we can see voltage steps to a value at some time later. I'm just setting up the level here to about 4 or 5 volts, 4 volts. So already we can see TDR going on, or reflection going on in that cable with an open end. And what it does is it makes a measurement of that when we press this button here. Oh, I'm just setting up time base, just expanding it, and then I'm going to press that button there, and it's going to make a measurement of that with the open end. There it goes. So it now knows where open is. Now I'm going to do what we call the correction, and I'm putting on a short first because that's what I've been asked to do. And look, here's TDR going on. The signal comes back down, and we're going to make a measurement of that so that we know where short is. Now I'm going to put, as instructed, I'm going to put the load on, a 50 ohm load. And when we press the button, we see we go straight to a straight line. So the fast step is now going through without any perturbation at all. Now, so I now know where 50 ohm matches in the middle, match is going to be about there, and then open and short. Now this display now is just of the mathematical function, a corrected function. And I'm just putting back, I'm just going to, this is just the open end, right? So now we've eliminated the pulse, that's what this little spike is, that's gone now. So we're now measuring the cable, that's the cable, and here is the open end. And we're going to call this the reference plane, i.e. the reference plane is going to be the end of this connector. And we're going to say that's the reference plane, open, short, that's the load on there, look. And then I guess I'll put the short on. Oh, I can see my display here isn't really showing the... what I've done is I've saved the traces of the open, the short and the load. But I can see my display isn't showing them very well here. There's the short going on by the looks of it.
Mark, do you want me to try a light off to see if that just improves it for this part?
Yeah, I can't even see it. Oh yeah, you can, there you are. So I've saved the open as a green trace. I've saved the load as a yellow trace. And I'm going to save this one as a red trace. Now, the reason I'm showing you this is because we're going to use exactly the same process to calibrate a VNA. So it's not a process that we need to be scared of, because we do it when we sell one of these pups. So open is up here, load and short. And then once we know these, we can measure any impedance in between, can't we? And that's what TDR and TDT does. We're able to measure networks with a fast pulse. Okay, is that one finished? I think it has. All right. Now, why is this important? Now, so what I've done here, the little switch, we can now operate the little switch at a kilohertz, right? And I've put in a kilohertz waveform, and I'm looking at a kilohertz waveform at all the taps along the cable. Well, don't forget, this cable was only 14 nanoseconds long, right? And so a kilohertz is rather low frequency, isn't it, right? And so this line length probably doesn't matter a great deal. But you can see I've got a kilohertz going in, I've got quite a clean waveform coming out, but all the way along the line I've got these high frequency spikes. Now the fact is that, you know, things with a kilohertz waveforms in probably don't have the bandwidth to see those or care about those spikes. So those spikes don't hurt anything when we're doing like an audio amplifier or a TV signal at megahertz or whatever. They don't really do anything. But here I've gone up to 4 megabit per second data. Now that's quite slow data actually, 4 megabit per second data. It really isn't very impressive data in a cable this long, is it? Now we've got a problem, look. My square wave has got all this sort of on it, all these distortions. So as the frequency of my square wave goes up in my cable, things start to go badly wrong in the presence of these horrible mismatches that we had at the end. And we start to get horrible ringing, and this can start to corrupt data. And this was only at 4 megabits per second in a piece of cable this long. So if we think about what USB 3 is, 5 gigabits per second, isn't it, right? So if we were using a piece of cable this long, we better not have mismatch at the end of our cables, otherwise we're going to be in dead stuck. So when we design the cable and when we design what it feeds at the ends, we better know all about the match at the ends. What do we need? Well, a network analyzer. And we can use the VNA or we can use the TDR TDT approach. At 500 megahertz or 1 gigabit per second, 2.8 millimeters of line length gets significant, and 0.4 millimeters of offset from a termination gets significant and starts to cause problems. Now just think about that, 0.4 millimeter. The poor engineer that is having to put, say, a terminating resistor right next to an IC might struggle to get it less than 0.4 millimeters away from the IC pin. So the digital engineer, or the high frequency digital engineer, has to worry about that only at 1 gigabit per second. And when you get to 5 gigabit per second, 0.1 millimeter or less. So mismatch matters, I would put it to you. All right, let's do another calibration on this 9311. We did a TDR calibration. We'll now do a TDT measurement. No, TDR. Sorry, I beg your pardon, I'm not reading the slide properly. What I'm now going to do, having calibrated TDR, I'm going to measure the TDR of both ports on this DUT. So I'm going to find something out about this DUT. So we take away our short circuit. We've saved short open load. And now we put the DUT on. Come on, Mark, get on with it. Right, so we put the DUT on and immediately we see there's an element of match going on here. So the DUT came from an open circuit and we can see the length of the DUT here. Now, I'm putting a load on the end of the DUT because if I'm measuring a 50 ohm device or some sort of device, whatever the device is, I better have a known termination on the end. And now what I can see is there's a tendency at really high speed edges, there's a mismatch. But it's not bad. As time goes on, this thing presents pretty good match. In fact, it's nearly as good as a cable or a terminating load. So it's got a high frequency mismatch on one port. We'll call that TDR11. We've measured port 1 and we put a signal into port 1 and we measured what came back off port 1. We'll call that TDR11. Turn it around. I've saved TDR11 so that we don't forget what it looked like. And I'm going to measure this now with this. There goes the DUT again. Don't forget I need to terminate it, because sometimes the termination can affect the measurement here. It doesn't in this case. But there you go. Right, so I've got there's two matches. They look pretty much the same, but they don't have, the mismatches don't have the same timing. Yeah, they're slightly offset from one another. So TDR11 and TDR22 are different, similar. Okay. Now, same thing, I'm going to do a calibration and a measurement of TDT. So this time, what I need to do is measure the signal going through the device. Let's do that. Doesn't take quite so long to calibrate for this. Probably need the lights off again if my lighting assistant. All right, so what I'm going to do is I'm just going to connect the two leads together. So I'm going to send signal directly from the pulse generator straight into the signal generator, into the channel, sorry, into the oscilloscope. And you can see It's a distorted pulse. This is all distortions of the pulse generator itself, not of the cable. And what we're going to do is we're going to calibrate that in a minute. Set the generator up. Select TDT. Voltage, and we're going to do a gain calibration. So what I want to do is, I'm going to call this unity gain, and I'm going to tell the instrument, the software, that this pulse shape is unity gain, and please now draw me a unity gain. Oh no, I haven't done it yet. Correction, I need to take out these pulse aberrations. Let's do that. And then it'll show me a unity gain network analysis. Okay, now, so if you can see the other yellow trace underneath, I'm going to turn this top one off in a minute. There you go. So it's now defined. That's going to be unity gain. This is naught gain. That's 1 gain. And this is an ideal edge shape here now. So we've now got an ideal pulse for our analysis of this network, this DUT that we don't know anything about. We don't know enough about it yet. Get rid of it. All right, so I've saved 1 and 0. No signal going through at the moment, so that's no gain whatsoever. Put the DUT in. Now, interesting. So this is the response to a step. Here is our 2 nanoseconds. We saw it, didn't we, on the scope? Well, we can now see it here. It's the same 2 nanoseconds delay, but on this high bandwidth scope, high bandwidth system with a high bandwidth stimulus, we can see that the pulse response of this thing, if you put an ideal pulse into it and you look at it on an oscilloscope, that's what you'd see as the pulse response of this network. I'm going to turn it round. I've saved that green trace, and I'm going to turn it round, make a measurement the other way. Oops. Thank you, Pico sample, go away. Okay, now that is exactly the same. So this device really is, to a very high frequency, reciprocal. The response is exactly the same in both directions. I'm just going to measure that, use the cursors, and we'll see it's 2 nanoseconds. So if we line up on the stimulus, the reference plane, the stimulus at the reference plane, and we measure the time to the output, and we can see, well, it's difficult to see, but it's coming up as about 2 nanoseconds. All right. Okay, now the rise time of that pulse was about 520 picoseconds. I did measure it, I forgot to film it. So it's about 520 picoseconds. So that thing, this thing has got about 685 meg bandwidth, something like that, if you use that simple idea that 350 over rise time equals bandwidth. Right. I've got video technician complaining about lighting technician. Get on it. Right. Next. So I'm going to just put those up like this as 4 separate measurements that we just made. We did 2 calibrations and we made 4 separate measurements, and we measured ourselves TDR11, the response at the input coming back off the input as a result of a signal on the input is that one. TDR21 is the response on port 2 as a result of a step on port 1. TDR12 is the opposite of that. It's the response on port 1 as a result of the step on port 2. And TDR22 is the response off port 2, coming back off port 2, reflecting from the mismatch of port 2 as a result of what we sent at port 2, the incident wave. Now I do it like this because we're going to see this over and over again on a VNA. We're going to see plots laid out like this, only they won't be these. They'll be S11, an S21, an S12, an S22, but they're the same measurement. They're exactly the same measurement done in 2 very different ways. So what we've found here is a through TDT21 and a TD12 characteristic and a time delay that we could not see. We couldn't really see it until we had the frequency content in the stimulus, i.e. our 20 megahertz bandwidth AWG source was not enough to see this detail. We've also found that the input and output match are frequency dependent, and that very fast signals see a mismatch, and that gets reflected. We didn't see any of that on a scope. We needed a network analyzer of some description. Now that reflection might be quite important, because the signal coming back at the source, it could damage it actually. If the source is a reasonably high power amplifier and it's getting signal back that is double the voltage it sent out in the first place, ouch! Yeah? And this is what happens on the national grid at 50 hertz. So we send out 400 megawatts down a cable, 100 kilometers long, 400 megawatts flowing nicely, load is absorbing it, yeah? And you then drop a tree across the 400 kV line and it shorts it out. Well, that 400 megawatts is going to turn round and come back at you. And that's what it does. And as it comes back, it breaks things all the way along the line, including if your house is on a tap off that line somewhere, your house is going to see several kV coming out of the mains. And this happens. And this is why we have safety regulations to make sure that we can withstand kV coming out of these things, right? The power station has to be corrected or protected against all this nightmare, and there's a massive industry around that, just protecting transmission lines. It's 100 kilometers long, it's a cable above a ground, it has an impedance, you better match it at both ends, and if you've got mismatch, you've got a problem. We're not interested in 50 hertz, we're interested in high frequencies, but it happens, it doesn't matter what the frequency is. In other words, you need to think, in some instances, you need to think about proper network analysis to understand what's going to go wrong. However, so we've learned a lot. We've learned a lot about this DUT, and many applications we've learned enough. There are many people out there that be quite happy with a TDR, TDT analysis, but for many there's a lot more to discover yet. So we are not yet wholly characterizing this device. Right, now a VNA. Yes, the VNA. Look, we're an hour in. We're an hour in, and we're going to talk about the VNA. The VNA makes makes the same measurement, but in a different way. So the TDR TDT uses a fast step stimulus and analyzes the response. Now, I've drawn on the board here, I don't know whether somebody can swing the camera around for me. Cameraman coming forward. Right, so what I've drawn on the board here, if we were to look at the frequency spectrum of our step, then what we see is from around a few megahertz, we see a spectrum something like this. It starts off very high, it ramps off quickly, but it's got little frequency components right out to 10 gigahertz. So when we put a step into a network, what we're doing is banging it with a ton of frequencies all at once. It's just a step, but it's every frequency in the spectrum out, in our case, out to about 10 gigahertz. What the VNA is going to do is this. It's going to put out 10 megahertz, and then in a sequence of steps, it's going to put out each frequency all the way, in our case, up to 6 gigahertz on the VNA. The benefit of this actually is, with this one, you really haven't got much signal available at high frequency. It's really quite small. And so the dynamic range we get into noise floor quite quickly. So when we're making these really high frequency assessments of our network, we're not hitting it with very much signal power. But a VNA is going to hit it with the same signal power at every frequency. This is very fast. We can do this with a single step. Not when we use a sampling scope, because a sampling scope is only going to be able to do one point at a time. So we're going to have to, if we want 1,000 steps, we're going to have to do 1,000 points in a trace. We're going to have to do 1,000 captures just because we're using a sampling scope. This is going to take longer, but if we want 1,000 steps, we're going to make 1,000 measurements. Now actually, this is still slightly quicker than this sweep here, even though we're one of the fastest VNAs available. All right, but we're going to go beep, 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 and we're going to sweep a frequency. So, yep, background, thank you. What I did here, this is a plot of the spectrums that come off the 9311 and the 9312. Now, this is not the spectrum we see on the board there. This is the difference between an ideal step and the 9311. So it's a bit wobbly, because you remember that pulse was a bit distorted. It's a bit wobbly. This is minus 5 dB, minus 10 dB, but we've got good content out to around 13, 14 gigahertz. But remember, it's actually very small. It's actually very small because the ideal pulse, it would be very small as well. So with a single step, we can stimulate the DUT with all the frequencies at once. Actually, the 9000 use multiple fast steps, given that we are a sampling oscilloscope. To make a VNA, this is what we need to do. And this is the simplest VNA that you can have. This is inside, it has a swept sine wave source, in our case 300 kilohertz to 6 gigahertz. And what we're going to do is, this is alien technology. This is a directional coupler, and the aliens didn't tell me how it worked. But it's kind of, you know, the old thing we did in the physics lab at school, the Maxwell's equations and laws, yeah, with the fields all at right angles. Well, yeah, if you can pick off the right fields, what you can do is you can say, well, the signal that goes in through this port will come out of this port, and any signal that comes into this port will go out of that port. And it also applies the other way as well. Well, it would if it was a true circulator. This is a directional coupler. So that's what's going to happen. The signal going through will come out here and go into the DUT. But if anything comes off here, it's going to go across there and out of there. And we can measure it. None of that is ideal, right? Nothing, it doesn't work exactly like that. There are isolation problems, and this is why we have to calibrate the hell out of the VNA. We have to calibrate all the errors in these couplers. What we're going to do then, we're going to pass it into a tuned receiver. It is basically an ADC. It's a variable gain amplifier, and it's a mixer. And we'll say a little bit more about all of those, but basically it works like a radio, a tuning radio. So if we're outputting a gigahertz here, we tune the radio to a gigahertz, and then this lot measures what comes out of the radio, you know, the amplitude of the signal, the amplitude, well, and the phase as it happens. We'll come to that later. That's going to measure our signal off port 1, and this one is going to measure our signal off port 2. And we'd then be able to do a TDR measurement, or a reflection measurement, and a transmission measurement, right? What I'm now going to do, I'm going to put a forward and reverse switch in the VNA, because you know what we want to do is measure the signals the other way as well, isn't it? So we can throw the switch over and measure that path through that directional coupler. Oops, where did that come from? Oh, I had to add that, didn't I? I had to add that because when I want to go this way, I've got to go through a directional coupler in there and out of there, yeah? But you can see I've now made a network analyzer that can measure in both directions, and there, so all of that is inside our box. It uses, this simple one uses 2 receivers, but in 2 sweeps I can get all the information I need. Looks pretty good. There's an important thing about these receivers. When we look at this signal with a tuned receiver, we can have a very, very sensitive arrangement indeed. So a radio receiver can work to very, very, very low signal levels and still recover the signal, because it does so by looking in quite a narrow bandwidth. And when we look in narrow bandwidths for what's there, we're going to eliminate noise. And so a tuned receiver can be working down to more than 100 dB down. Now 20 dB down is 10 times down, isn't it? And 40 is 100 times down, and 60 is 1,000 times down. So 120 is 1,000,000 times down, right? So you can have a very, very sensitive receiver here if it's a tuned receiver. Now, unfortunately, things aren't quite as simple as we'd like, or if we use just 2 receivers, we'd have a lot of inaccuracy, because the signal that a synthesizer can produce, they're not terribly accurate in their level. So if you look at signal generator specs, you'll see specifications around 0.5 dB flatness or 1 dB flatness. Well, that's 10% error if there's a flatness error that's that big. We need to know this signal much, much more accurately than plus or minus 1 dB. So we're going to introduce further receivers. So when the switch is over here, we're going to split the signal, divide it into 2. We're going to pass that to the DUT, and we're going to measure it here. So the accuracy is going to be this receiver here measuring the signal that is going out. And we're going to call the signal going through here, whatever it is, we'll call it the A wave. We're going to call it the A wave because remember, we've already said the A wave is going to be the incident wave. So the A wave is the incident wave that comes out of the VNA and hits the port on the DUT. When we transfer over here, we've got another receiver over here. We've now got 4 receivers measuring the A wave on port 1, the A wave at port 2, the B wave, whatever comes out of the port on port 2, and the B wave on port 1. A quad RX receiver. What some people do is they don't put 4 receivers in, they put, say, 2 receivers in and they use a switch. Or they put the switch over here, or you even see 3 receiver designs. The trouble is, when you do that, there's always the error of the switch, and you can never cal it out. So it's really rather nice to have 4 absolutely identical receivers, not that too far off from a 4-channel scope. Now, when we mix these signals down, if we're outputting, say, 3 gigahertz as a tone, and then we, at the mixer, we inject, say, 2.999 gigahertz, then the output from the mixer will be a 1 megahertz signal. It'll be a 1 megahertz signal of around the of the same amplitude as the signal that is being received. So the signal being received is this 3 gigahertz signal, but we've mixed it down to what's called an intermediate frequency, and we've made a megahertz signal that is the same amplitude, or represents the amplitude. Now, a 1 megahertz signal we can put into a 100 megasample per second A to D, a scope. So that's essentially what we've got here, a 4-channel scope with mixers on the inputs. Now we could have mixed all the way down to DC. We could have mixed down with a 3 gig tone all the way down with a 3 gig into the mixer. We could mix all the way down to DC. We don't do that, because if we do, we get down into DC offset, causing all sorts of fluctuations, flicker noise. So what you want is an IF frequency that is relatively high, so that you don't get into 1 over F or flicker noise of all these components. So a scope can't do that. A scope has a noise floor that is what? 80 dBs down, something like that in our case. Yeah, something like that. You're never going to get down to 100 dBs because of flicker noise and all that you see in a DC coupled scope. But at a megahertz you can get right down to those sort of levels. I'm just going to add there, I've added a couple of bias Ts, and then you've got the full architecture of our scope. Sorry, our VNA. Bias Ts, what are they all about? Well, if this DUT was an amplifier, say a transistor, it might be a transistor on a board, I might have to provide some power to the transistor on the board, and in RF amplifiers you can do that through its output. Yeah? So I could feed the power to the amplifier through the bias T. And this is what people do when they're testing active devices. So bias Ts are really quite important, and they're usually quite expensive options on most of our competitors, or they're not available at all. But they are available here, and they're not there, and we don't charge for them. So bias Ts, so that we can inject this would be a bias for the gate or the base of a transistor, and this would be the bias for the collector or the drain. Yeah? So that's for injecting, it can be test signals, control signals, whatever, onto the ports. And that's the architecture of our VNA. That's what it looks like. And you can see how it works. This is a good scope. We can use these wonderful Pico scopes with huge memory. This waveform here in the zoom window, this is start of sweep. It's a sweep trigger signal coming out of the back of the VNA. Start of sweep. And that's the end of sweep. And on this particular, this was a what, 200 meg scope? I set this up with a 250 megahertz sweep. So it's going to sweep from, say, 300 kilohertz to 250 megahertz. It could go a lot further in the case of the VNA, but we'll keep it down, right? So, and this is the signal that comes out of port 1, and this is the signal that comes out of port 2. And you can see it doing the sweeps. Yeah? And in fact, that's the bandwidth of the scope. That's it. That's the bandwidth of the scope, and it takes boom to get it. Yeah? So we'll have VNAs on our Banshee systems in not too distant future. But let's zoom right in on those waveforms here, and we see this. I've zoomed right into the trigger point. Oh, sorry, zoomed right into the trigger point, and this is what's actually happening. We're outputting from port 1, and then we're outputting from port 2. Now we could have done this differently, couldn't we? We could have done an entire sweep on port 1 and an entire sweep on port 2. But because we're using an electronic transfer switch, we can switch between the two ports. And so the way it actually does it is it does both sweeps synchronously. Outputs from port 1, port 2, port 1, port 2, port 1. And we're doing what, 50 microseconds per division here. So 100 microseconds, it's got its first measurement. And 150, just over 150 microseconds, it's got the second measurement. So it can do two sweeps in around 170 microseconds. That means it can get an S2P point in around 170 microseconds. That's where our 5,000 S2Ps per second comes from. Now, most of our competitors, they specify measurement rate, so be careful. When somebody says they do 3.4 measurements per second, one sweep. So it's actually 1.7 measurements per second when it comes to the full S2P. So we're making both measurements in 170 microseconds, and hence the fast update rates that you were able to see earlier. And that actually runs as a video, I seem to remember. Whoops. Why doesn't it? It does. I'm sure it does. Yeah, there you go. This is a software time. Yeah, so you can see that each sweep start, there's a bit of a software latency, as it were. And here's the update rate that is occurring. You can see that's quite lively. You're getting about 20, 25 updates per second on the screen in terms of a whole trace on all 4 S parameters. Okay. Pros and cons. I think I've mentioned most of these. Pros and cons of the sign test. All frequencies tested at the same relatively high spectral power. Direct realization of frequency domain measurements. So I didn't mention that. We're going to be able to get S parameters directly from frequency domain measurements. Tracking receivers can have very high sensitivity, so we can have a very low noise floor. Automatic forward and reverse switching integrated to the majority of VNAs. Could be slow though because of all these points having to be done one at a time. Important to have fast stepping and settling. We may have to trade sensitivity, bandwidth, for speed. Yes, so the bandwidth in which we're looking at the signal, if we make that very narrow, like 10 Hertz, then we're going to have to wait for things to settle before we can measure it. So if we're going to measure something in a 10 Hertz bandwidth, the amplitude of the signal for instance, then we're going to have to wait for 0.1 of a second before it settles so that we can make a measurement. So if we put the bandwidth right down low to get really deep noise floor, then we're going to have to slow the sweeps down, otherwise the sweep's going to go too fast, right? So the VNA automatically adjusts its speed to the bandwidth settings. We'll see more of that. Now what we're going to, sorry, I haven't finished, have I? Pros and cons of fast step stimulus. Very fast, all frequencies tested at the same time. Direct realization of time domain measurements. And so very quickly you can get distance to fault. So TDR and TDT are very good at finding if there was a short circuit on the end of this. That's the quickest way to find it, and how far away the short circuit is so that you can go and fix it. Yeah? So very quick at that sort of measurement. It's a broadband measurement, so the noise floor is limited and you'll only get about 50 dBs of dynamic range. Automatic forward and reverse switching typically not provided. There was one TDR, TDT, VNA from LaCroix, I think, that included the switching, but most solutions don't, and ours don't. Right, now I'm just going to bring you back to our tapped line. There it was. Tap line. It had 8 taps along it. This time, instead of putting those square waves in, I'm going to put the sine waves in. Oh, this is interesting. So this is what happens on each of the taps along my line. Some of the taps have got virtually no signal on, and some have got quite large signal on. What? So this is different, isn't it? And this is different because we've got a continuous sine wave going along the line and a continuous sine wave reflecting back along the line, and the two are working together and doing stuff. So along the line, if we've got mismatch, we might make the signal disappear altogether. Ooh, that's going to be nasty, isn't it? Right? So you can see why mismatch is getting really, really important, right? And I don't know whether you'll, whether your minds will follow this through, but if I was to sweep the frequency of the sine wave, and here it is, 1 megahertz through to 100 megahertz in this line. If I sweep the frequency, this is the response of each tap. They all have this huge peak in them, and this is the output level. The output level is, it was 90 ohms feeding 10 ohms, wasn't it? So the output level is going to be somewhere down here. And this is what we see, by the way, at the load. Oh no, this wasn't 90 ohms. Haven't got it on the slide, have I? What the mismatch condition is. Damn, I'll sort that out. Anyway, what we're seeing is a response that at certain frequencies each tap can be naught, or quite low. Right, there's a little animation in here. There's all sorts of animations on the web to show you how what this looks like. I'm going to try this one. There you go. So this is my, oh, you could do me a few more than that, couldn't you? There's my blue wave going along, forward along the line, and my red wave coming back. I don't know why it's not, oh, gold. Don't know why it's not, there you go. And what we're seeing is at certain points along the line, we never get any signal amplitude. This black is the amplitude of the signal along the line. And at some points we get nothing, and at other points we get peaks. Yeah? In this mismatched line. And there is a defined measurement here. The voltage standing wave ratio, or the standing wave ratio, Vmax over Vmin. So in this particular case of total reflection going on in the line, VSWR, Vmax is large, Vmin is naught, infinity. Yeah? So standing wave ratio is one of the measurements that our network analyzer is going to be able to provide for us. And I've drawn out, or Wikipedia does for me, it draws out several examples here where Vmax and Vmin are variables. So this is quite a badly mismatched line. If we do the maths on it, you can measure those, and it's a 4.7 to 1. The standing wave ratio is 4.7 to 1. Pretty bad match, that is. VSWR 2.3 to 1. And what's this one? This is 9 to 1. This is really, really bad. Ooh, ouch. Yeah? So match is pretty important to us. Sine waves or high frequency data. Applying different match conditions to both ends, what I've done here is there are 3 different match conditions. This is a bad one, 85 ohms and 15 ohms. So you can see that with this bad match condition, the flatness, this is the flatness in the line, or at the various points in the line, even at my load, look at this. The load response is not flat because of mismatch. So I wouldn't get the same signal out of the end as I sent in. If it comes down to 60 and 40, which is pretty typical actually, that's, you know, this is pretty much most lines you see are matched something like this. You can see even then, in the red line, in the load line, there's a little bit of ripple. And very good match, 51 ohms and 49, you can see that all the way along the line we're getting pretty flat responses and through to the load. Yeah? So good match, essential. Right, here are some potential outputs on a VNA from our DUT. And now all of these plots are a plot versus frequency. We're going to call this one here, we've heard it before, S11. This is, I'm going to use a log scale here. This is log magnitude, frequency from 5 megahertz to 6 gigahertz. This is the reflection off port 1 due to the incident on port 1. You can see the reflections from my DUT start off lowish and then they get high. I mean, up here at naught, the signal coming back off this device is the same as the signal that was sent to it. It's rejecting the signal altogether. It's coming straight back at me. This is the signal that comes out of port 2. Here it says at low frequency the signal is the same as went in, 0 dB away from the input, and then it rolls off steeply. Oh, and I can see all the way down here, look, minus 90 dB, and then something happens and at higher frequencies it comes back up again. So already I'm seeing a lot more about this DUT, aren't I? I couldn't see down to minus 80 dB. I didn't know this thing went all the way down here. I certainly didn't know anything about this little response here. So I'm finding out more about my DUT. And we can see that the response on port transmitted through to port 1 due to the incident on 2, so that's the forward wave, this is the reverse one. We can see it's identical. And this one here, this is the equivalent of this, but on port 2, reflection coming off is pretty low, minus 20 is pretty good, and then it all comes back. So horribly mismatched. Do we know what that is yet? What is it? It's a low pass filter. It's a low pass filter with an AC coupling. You remember the scope found that down at low frequency it was AC coupled. Yeah? So that's how I actually put a DC block capacitor. That's the 220 nanofarad capacitor that the DMM measured, right? So we do know what this thing is now. The rejected HF signals are 10,000 times smaller than the signal level here. So we're putting the same signal in at all frequencies, and what's coming out is 10,000 times smaller. That's what minus 80 odd dB is. in voltage terms, and it's 100 million times smaller in terms of power. And we can still see it. But there's still some more information to know, because this quad RX receiver, it's not just one A to D, it's two. And we won't go into exactly how, but what these two A to Ds do is they get what we call the in-phase signal and the quadrature signal so that we can get the vector magnitude and the vector amplitude, magnitude and phase of the signal that's coming back, or the signal on the receiver. So this not only measures, see, a scope just measures the amplitude of a signal, doesn't it, versus time. But this is going to be measuring phase as well, and it's going to do it in the form of an IQ signal. See the next slide in a minute. It is the next slide, yes it is. So these waves, the A wave, the B wave on port 1, and the A wave and the B wave on port 2, they're all actually going to be vector quantities. So we need to start to get used to some data that is different from that of a scope. So just a reminder here, any sine wave signal that we're measuring could be represented as a vector, where the vector is the amplitude, and it has an amplitude, and it has an angle, a phase. So what we mean here is we have a phase with in relation to the other signal, the source signal. So we have vector amplitude and angle, and the way we can represent that is with a real or an in-phase component, the I component, the in-phase component, or the imaginary or the quadrature phase, the Q component. So whereas a scope gives us data like this, it has lots of information in a header file. If you save a trace, this is a Pico sample trace, you have a ton of data in the header here, and then you have point by point, you have the amplitude on the screen, and it goes on for 10,000 points or whatever, yeah? When we get data off one of these filters, we're going to get data like this, receivers, we're going to get data in this form. We've converted it to frequency, and then a magnitude and an angle, and then the second measurement. This is one measurement, the S11, and this is S21, a magnitude and an angle, and there's more over here. So all the waves, all the data that we're going to be talking about, the A wave, the B wave, the S parameters that come from the A wave and the B wave, they're all vector quantities. They all have a magnitude and phase, and they're originally measured as a real component and an imaginary component. Right, so now I'm going to look then at some of the data. Given that we've got magnitudes and angles, we can start to derive several traces on our VNA. Several different types of plot that we can choose to display for each of the parameters. So this one, for instance, now I'm going to start over here. This one. This is S11 magnitude only, linear magnitude. Yeah, and you can select this. Here you are. This is the menu that you use to select it. I could go S11, pull that down. Oh, what's this one? No, this is S21. S21, drop that menu down, and you'll find linear magnitude. And if you do that, you'll see this plot. Now this plot relates quite nicely to what we did with our picoscope. So with our picoscope, we did this blue and the red over 20 megahertz, and we found out what the gain was and how it changed over 20 megahertz, didn't we? So that red bar there represents that sweep. Because this goes out to 6 gigahertz, right? So with our scope, we could have found this. And then what we did with the scope information, we drew a line, didn't we? We drew a line that was the gain. And that's what this is. This is what happens as for this DUT. This is what happens. The linear gain goes on, it falls away gradually, and then it comes to, what's this? It's about 700 megahertz or so, and it goes whoa, off a cliff. Yeah? And so that is our equivalent to our scope network analyzer. Now, it doesn't tell us that much because we can't see anything along here. There's nothing going on out to 6 gigahertz, right? So that plot is of limited usefulness to us in the context of a VNA. Let's instead change this scale to log, in which case that whole bit there, you'll agree on a scope you can see 1 down to 1%, say. And if you map 1 down to 1%, across here it maps to 0 to minus 40 dB. Yeah? So this part of the curve is that. That doesn't show you this. Yeah? So this is log magnitude by frequency. All I do is just go boom, log magnitude. Yeah? And I get that plot there. So that plot and that plot are directly related to one another. All these plots in the top half, by the way, all these plots are sensible for what we call the transmitted parameters, the parameters that go through, transmit through the DUT. And these down here relate to the reflected parameters. I'm going to change the slide and we're going to relate a couple more things. So, back to our linear one. This is our linear plot, and this is a plot of phase by frequency for the transmitted parameter S21. You can see phase starts off at around 0, goes down negative to minus 180 degrees, back, boom, 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 plus 180, minus 180, cyclic. Then it goes all noisy. Why does it go all noisy? Why am I not getting any sensible measurement here?
Low amplitude.
Low amplitude. Look, I'm down in the noise floor here. So what I'm capturing is noisy signal, and I'm finding it hard to distinguish what the phase is of two noise or one noisy signal. One of them's very low. The input's very high, but the output's very low. So this is correct. I cannot get phase. You can see when it comes back up again, look, I get it again. So this, we should expect phase to be noisy if the signal amplitude is very low. What would I have to do to improve the noise? Any ideas yet? Mentioned it a couple of times. Okay, I could change the bandwidth of my acquisition. I could drive bandwidth down to say 50 hertz, 10 hertz, and that noise floor will go down. You'll see. So, phase. Now, let's map that to a polar plot. So this is a linear polar plot of the same information. This is all the this is the magnitude of a vector, this is a phase of a vector. Let's put it on a polar plot, and with the circle at 0 and the circle at 1, that maps to a circle there. Yeah? So at very low frequency, no phase shift, gain of 1, there it is on our polar plot. And as frequency increases, what happens first? Look, this comes down to minus 180. This hardly changes at all. So what happens is this plot goes around here, minus 180. And then what happens? So it flips, oh yeah, it goes round to plus 180 and then starts to reduce and come back to 0, yeah? And so we can follow this all the way. When we get to this point here, magnitude starts to fall away. So this is saying we're going round and round this circle, and then it starts to spiral in to the middle. And by the time we get here, we've got no signal and we're there. So that plot is a plot of the same information, but and it enables us to see how phase moves. And then if I don't know whether you can get your head around this, but if this plot does that, and we were to look at it from down here, yeah, if you were to look at it, right, what would you see? You'd see this plot here. Yeah, the in-phase component going up and down, i.e. yeah, that's the in-phase component. And then if I can't climb all over there to do the same there, but if you look that way, you'd see this quadrature component. It goes negative first and then. So this is the real part of my vector, and this is the imaginary part of my vector. So all of those are closely related. Yeah? Okay.
Just the term group delay.
Get off!
Sorry.
Hold your horses. Group delay.
I'll set them up.
Yeah. Right, so with our low frequency scope, we were able to see this 2 nanoseconds, weren't we? And we also saw it, although it's a bit blacked out here, we also saw it on the Pico sample display, the TDT display. We saw that 2 nanoseconds. That's that 2 nanoseconds. That's on 2. I don't know whether you can see, that's 0 and that's 2. It's measuring a group delay of 2 nanoseconds at low frequency. In other words, all low frequencies are delayed by 2 nanoseconds. Now, this is interesting. As frequency goes up, the signal gets delayed a bit more. Ah-ha-ha. So if we were to take a little group of frequencies, down here they're delayed by 2 nanoseconds. Up here they're delayed by 4 nanoseconds. Yeah? Why is that important? Well, why does it happen? Well, I'll come to that as well. It's on a slide later, actually. But what it is this. Do you see how? Right, this is phase, and it's incrementing linearly, isn't it? And if I did what's called unwrapped phase, this is wrapping round a circle, isn't it? So this is wrapped phase. It's going round and it's coming round the circle. We came round the circle, didn't we? But if instead I unwrapped it and I called it and I went further up in degrees, so as I go around the circle, I go 360, 720, yeah, circle after circle. You can see I'm going a linear line of unwrapped phase. But here, look, the slope changes. So as I roll off, the slope changes. And if I was to measure the slope, I differentiate the waveform, that's what this is. It's differentiated phase. And so phase slope is constant, 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 whoops, goes up. Yeah? So group delay, that's what group delay is. It's the rate of change of phase. The rate of change of phase. Now, all right, that's a complex notion and it's very hard to get our heads around what that means, right? But let me tell you this. If I use my mobile phone and I output data from the mobile phone, my voice in the sense of data, it goes as a modulated signal, yeah? And the modulated signal has a bandwidth. So some of the data is being encoded at these frequencies and some of it's being encoded at these frequencies in the bandwidth, yeah? if the bandwidth was that bandwidth there, some of my data would get delayed more than the other parts of the delay of the data. Ouch, right? So it's very important in a communications channel, when you're having a modulated signal of any kind whatsoever, if different bits of the data are in different parts of the spectrum, you better have flat group delay. Because otherwise your data stream is going to get right corrupted simply because it's out. I mean, 2 nanoseconds is like huge in high-speed data, isn't it? Yeah? So different parts of the data in different parts. So this is, group delay is really, really important to communications engineers, anybody that wants to keep the signal aligned. Now the other thing it does, you remember I said our step has this frequency, this spectrum. So what happens, you know when you add all these bits of spectrum up, I'm sure we've all seen it in terms of a square wave. We draw the fundamental, and then we draw, what is it, third harmonic. Yeah, and we draw fifth harmonic. Oh, it's getting hard. Oh, I don't know. Anyway, they all of the sorry, I've not drawn this quite right, but all of the harmonics add to make my square wave, right? But what if some of them were delayed by 4 nanoseconds and these were all delayed by 2 nanoseconds? Oh God. All these harmonics are going to start to misalign with one another. And this is what happens. Seen that before? Group delay. So, and we saw it, didn't we? We saw it on our pulse when we looked at, here it is, look. The pulse shape has been corrupted because it's barely, yeah, you'll have to remember it's not very visible here, but yeah, we had this ringing, and this is due to the way the filter rolls off and the fact that group delay is sliding all the harmonics with respect to one another. So if we want to keep our data I nice and clean, we better not have this particular DUT in our signal path. It would be highly destructive. Yeah, so no thank you. Oh, I didn't do this, but whoops, sorry, back. Now, this one is the time domain plot. Here it is again, look, here's the ring. And that is directly the same as that. Now, what have we done here? All we've done is a vector Fourier transform on the S21 data, and we've converted it to the time domain. And lots of you here have heard us talk a lot about, can we have S parameter analysis on the 9311, i.e. convert from the time domain? Yes, it's all possible, right? But we don't have it. Here it is. This has the transformation embedded within the Vector Network Analyzer. Okay, so what's that? That's 8 plots. We've got 8 plots, all of the same data that are useful in different ways in analyzing networks. And now we'll move on and we'll come down to these. These are the reflection ones. This is horrible, isn't it? But there you go. Right, this one here, this is the Smith chart. Smith charts, lovely. We're going to learn about Smith charts in the next presentation. But here's a zoom of it. It is a polar plot. I'll tell you all about, this is the grid. Forget that. It's just the same as this polar plot. It's a polar plot of S11. Well, not quite, but we'll come to that. But essentially, it's the same as that over there. But it's got a grid on it, which is the Smith grid. And we'll talk about the Smith grid in the next talk. So, here we go. We can do the same thing as we did last time. We've got S11 magnitude here. and we've got, this is log magnitude, and we've got S11 phase here, yeah? And we can map, we can start at these 2 points here. This is quite small, this is minus 20 odd dB, quite small, and a little bit off in phase, and it maps, here you are, right pretty close to the center of the Smith chart. So I said, well, minus 20, that's a pretty good match. The center of the Smith chart is good match. Yeah? And then as we slide along in frequency, you can see this magnitude comes up and down, but it's still quite small. This is a log scale, don't forget, so these are quite small movements actually. And phase increases. So again, look, as we go up in frequency, we go around like this. And then as we come to this point, as we come to the roll-off, look, the reflection starts to get bigger in magnitude. It's still sliding around in phase. So here it is, it spirals out. And it comes to the circle of mismatch. So it started at the point of match, and it spiraled out to the circle of total mismatch. Yeah? And we'll see more about that next time. So that's how those two plots relate to that. And you might remember we talked about standing wave ratio earlier. That's the standing wave ratio. So what that's telling us is, in this line, Vmax over Vmin. Or no, not in this line, sorry, in this dot. In this dot. It's telling us Vmax over Vmin. It's pretty small, i.e. the Vmax over Vmin 5 to 1. Can't read the numbers now. Ah, damn. Never mind. Anyway, this is the match condition, and sorry, this is the mismatch condition, and then the match condition. Somewhat wrong there. Anyway, standing wave ratio. I'm not sure I quite understand that plot. Right. Who needs to know? Who wants all these measurements? Well, where should we start? Microwave applications. Now, microwaves, high-speed data and high-speed signals have really found their way into just about every electronic sector there is, haven't they? Gradually, it used to be, 20 years ago, 30 years, how many years ago? 30, 40 years ago, 30 years ago, 40, when I started. You know, microwave engineers, there really weren't many, and they only worked on radio stuff basically, and pretty much nothing else. But things have changed a great deal, such that microwave application, gigabit data pipes, telecoms, radar, short, long, penetrating, and guidance. There are so many radars now. Last ARMS conference, they're taking, that I went to, they're talking about radar for your touch screen. So at the moment you have to touch the screen, don't you? But a little radar system in the screen would be able to pick up gestures. Short range radar will be on your touch screens within a year or so. Probably already is in some areas. So short, very short wave, long penetrating and guidance radar imaging. We can send signals out. It's a bit like if I send out a light wave, I can illuminate something and I can see it, and I can see it in quite a lot of detail because light's quite high frequency. But I can send out microwaves, and if I'm able to measure what comes back, I can see things that perhaps I couldn't see otherwise. And there are instances, certainly LA work with a company, so our partners work with a company where they detect breast cancers simply by shining microwaves in from a VNA, picking them up and getting them back, and they can create an image of a breast cancer, yeah, with the microwave. There's another, we've had an interest from somebody designing mine detectors, high-speed mine detectors. So you send out a microwave signal into the ground. What comes back tells you whether there's a block of metal there. And if you're fast enough at doing it, the soldier will be able to sweep quite quickly, won't they, right? So a VNA with 5,000 points per second measurement is quite handy. Put the VNA in the backpack, it's portable. Put the VNA in the backpack, you're going to have quite a fast metal detector, aren't you? Yeah? So it's not just microwave engineers, it's people trying to, they're trying to use radio solutions in so many things now. Metallurgy and civil engineering, RF heating and energy transfer, particle acceleration and detection, the scientific industries, astronomy clearly, tracking, location, distance, depth, velocity and RFID. You know, all of these applications are microwave applications. And
quick question, I don't see anything to do with antenna testing. Have I just missed that?
well, no, you're not. It's simply these are the applications, and of course antennas are part of that. And an antenna is just a DUT. But you're quite right. That's a very, very important DUT. What does it do? It takes an electronic wave or electromagnetic wave from a piece of cable, and if you make your antenna correctly, you're going to inject that into the ether. You're going to match it to the ether. Yeah? So, and if the antenna were not correctly matched, you get the signal back instead of it going to the ether. So it's another DUT for a VNA. You're quite right. Yeah. Market sectors then. Direct, using VNAs in a standalone type situation. I think all the market sectors are here. The obvious ones at the top: semiconductors, interconnect and substrates, consumer, home and wearable and personal tech. You know, even the fashion industries are now having to think about circuitry within the clothing, and a lot of that's microwave circuitry, RFID type circuitry. Power and energy, higher education and training, hire and rental companies, resellers, i.e. if you're a reseller then you need to test goods as they come in, or you need to provide service for goods. Calibration and installation. Installation engineers can go to site and they can measure the HDMI feeds and the network feeds that they put into your house. They can measure those and make sure they're good before they leave the property, can't they? So installation engineers as well. Indirect users. So these are people that embed VNAs into their equipment. ATE, an in-circuit test. Heavy usage, very heavy usage. Medical applications where the VNA is built into an imager. Agro, bio, pharma and food industries, chemical, minerals, material science, civil and mining. Really, microwaves and VNAs, potentially, they're general purpose test equipment. A bit like saying, who uses a scope? You know, what market sector analysis can you do on a scope? Well, everybody, right? Who uses a VNA? Well, if you make them fairly easy to use and you make them at a low enough cost, then they are a general purpose device. VNAs and measurement users, the people that use them, well, obviously engineers and technician. Design production. If you're producing cables, you need to measure the cable. Each one that you make needs to be measured. VNA. QA, installation and service. Scientists and researchers. Trainers and educationalists. They'd really like every student to have a VNA, and I think a lot of our inquiries are coming in from universities and colleges wanting to equip every student with a VNA. System and software integrators.
Quick question, Mark, on the application. So as we know with scopes, a large number of our customers build scopes into their kit and it becomes a part of the system. So is that just the same with VNAs as well?
Yeah. Yes, VNAs are quite regularly built into. VNAs are also called reflectometers. A reflectometer can only has one port and it only measures S11. But that often is the only measurement that you need. And this is low enough cost, it's still cheaper than reflectometers, right, or others. So yes, these things get built in and automated or remotely controlled within that use, yes.
And there is a software development kit.
Yes, on the way.
Along the lines of
our man at the back there, or our men at the back there. I'm sorry. Yes, they're working on something for us there.